This is section 5.1, part B, myths about randomness. The idea of probability seems straightforward. It answers the question, what would happen if we did this many times? In fact, both the behavior of random phenomena and the idea of probability are a bit subtle. We meet chance behavior constantly, and psychologists tell us that we deal with it poorly. The idea of probability is that randomness is predictable in the long run. Unfortunately, our intuition about randomness tries to tell us that random phenomena should also be predictable in the short run. When they aren't, we look for some explanation other than chance variation. So you toss a coin 6 times and record heads or tails on each toss. Which of the following outcomes is more probable? Head, tail, head, tail, tail, head, or tail, 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 head, head, head. Both of these outcomes are actually equally likely because they have 3 tails and 3 heads. In each toss, you have 50% chance of getting a head or a tail, regardless of what you got on the previous toss. So even though most people would answer that this first set is more probable to happen, both sets are equally likely to happen. Believers in the law of averages think that if we toss a coin 6 times and get 6 tails, the next toss must be more likely to be a head. It's true that in the long run, heads will appear half of the time. What is a myth is that future outcomes must make up an imbalance like 6 straight tails. Coin tosses and dice have no memory. A coin doesn't know that the first 6 outcomes were tails. It can't try to get ahead on the next toss to even things out. So even though those first 6 tosses were tails, the coin still has a 50% chance that the next toss will be a heads and a 50% chance that the next one will be tails. So the probability the next one is heads is still the exact same probability that it would be a tail. Belief in this phony law of averages can lead to serious consequences. A few years ago, an advice columnist published a letter from a distraught mother of 8 daughters. It seemed that she and her husband had planned to limit their family to 4 children. When all 4 were girls, they tried again, and again, and again. After 7 straight girls, even her doctor had assured her that the law of averages was in our favor 100 to 1. Unfortunately for this couple, having children is like tossing coins. 8 straight girls in a row is highly unlikely. But once 7 girls had been born, it is not at all unlikely that the next child will be a girl. There's still a 50% chance that the next child is a girl. And it was. Simulation is the imitation of chance behavior, based on a model that accurately reflects the situation. We can summarize this process using our familiar 4-step process, which remember is state, plan, do, and conclude. When you're performing a simulation, you need to do your state first. So what is the question of interest about some chance process? Then you need to plan. Describe how to use a chance device to imitate one repetition of the process. Explain clearly how to identify the outcomes of the chance process and what variable to measure. Then you're going to do the do. This is where you perform many repetitions of the simulation. And then finally, you will conclude by using the results of your simulation to answer the question of interest. On your AP exam, you may be asked to describe how you will perform a simulation using rows of random digits. If so, provide a clear enough description of your simulation process for the reader to get the same results you did from only your written explanation. So in a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at the school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. entrance. Last month, the winner tickets were drawn by a student council member from the AP Statistics class. When both golden tickets went to the members of the same class, some people thought the lottery had been rigged. There are 28 students in the AP Statistics class, all of whom are eligible to park on campus. Design and carry out a simulation to decide whether it's plausible that the lottery was carried out fairly. So the first thing we need to do is make our statement or our state. So we can say, what's the probability that a fair lottery would result in 2 winners from the AP Statistics class? Next, we need to make our plan of how we are going to run this simulation. So we'll use Table D to simulate choosing the golden ticket lottery winners. Since there are 95 eligible students in the lottery, we'll label those students in the AP Statistics class from 01 to 28, and the remaining students from 29 to 95. Numbers from 96 to 00 will be skipped. Moving from left to right across the row, we'll look for a pair of digits until we come across 2 different labels from 01 to 95. The 2 students with these labels will win the prime parking spots. We will record whether both winners are members of the AP Statistics class with a yes or a no. So for the do part of this, we're going to perform repetitions of the simulation. We'll use Table D, and we're going to start on line 139, and we will have to continue on to line 140. The digits from rows are shown below. When drawing vertical bars to separate the pairs of digits. Underneath each pair, we mark if the student was in the AP class with a check mark, and if they're not in the AP class, we will put an X. If it's a number that's not between 01 and 95, we will write skip below it to know that we don't need to use that number. And if we have 2 numbers that are the same within a set of 2, we will also skip because of repetition. So here's our list of digits. We have 55, 58. So in that first repetition, neither one of them were in the AP Statistics class, so we would write no. Then we would look at the next 2, no. The next one we have 1, but not the other. And we will continue doing this until we get about 18 to 20 trials. After 18 repetitions, you can see that we had both people in AP Stats here, both people in AP Stats here, and both people in AP Stats here. So there were 3 times out of the 18 repetitions where both winners were in the AP Statistics class. So for our conclusion, in our simulation of a fair lottery, both winners came from the AP Statistics class in 3 out of the 18 simulations, which is 16.7% of the repetitions. If we reduce this means for about 1 out of every 6 times the student council holds the golden ticket lottery, this will happen just by chance. It seems plausible that the lottery was conducted fairly. In an attempt to increase sales, a breakfast cereal company decided to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the NASCAR drivers, Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. The company says that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 driver's cards. She is surprised when it takes her 23 boxes to get the full set of cards. Should she be surprised? Design and carry out a simulation to help answer this question. So again, we're first going to start with the state. So what is the probability that it will take 23 or more boxes to get a full set of 5 NASCAR collectibles? Then we're going to come up with our plan. This time, let's use our calculator instead. So we need 5 numbers to represent the 5 possible cards. We'll let 1 represent Jeff Gordon, 2 equal Dale Earnhardt Jr., 3 is Tony Stewart, 4 is Danica Patrick, and 5 is Jimmy Johnson. We'll use the random integer from 1 to 5 to simulate buying 1 box of cereal and looking which card is inside. Since we want a full set of cards, we'll keep pressing enter until we have all 5 that are labeled from 1 to 5. Now, it is possible we would not skip any repetitions because it is possible you would buy 1 box as Jeff Gordon and the next box you buy also has Jeff Gordon in it. We'll record the number of boxes we had to open. So in this do process, we would write down how we did the simulation. So the first time, we got a 3, 5, 2, 1, 5, 2, 3, 5, and then we got a 4. So it did take 9 boxes. You would keep doing this. Each time you would have to keep hitting enter until you got all 5 of the numbers and then record the number of boxes that it took. If we were to do this 50 times for the simulation, this dot plot represents how many boxes of cereal were required. So for all of them, it was between 5 and 22 boxes. So we can conclude that we never had to buy more than 22 boxes to get the full set of NASCAR driver's cards in 50 repetitions of our simulation. So our estimate of the probability that it takes 20 or more boxes to get a full set is roughly 0. The NASCAR fan should be surprised about how many boxes she had to buy. So what do these simulations tell us? For the golden ticket parking lottery, we concluded that it's plausible that drawings was done fairly. This does not mean that the lottery was done fairly. It just means that it is possible that it was done in the correct way. It takes our NASCAR fan 23 boxes to complete the set of 5 cards. Our simulation says that it's very unlikely for someone to have to buy 23 boxes to get a full set. This does not mean that the company was not telling the truth. The NASCAR fan might just be very unlucky.